have the lighting you guys do.
Uh,
Actually, hold on a second. Let me get my wife here, so I don't have, so she can do it, and then I can. Hey Pam, can you come here for a second? Hey, how's it going, Bill?
Not bad. How about yourself?
Good, good. I just talked with our mutual friend Sharon Majumdar, who's getting ready to go to England.
Yeah, he and I Zoom drink every Friday or Saturday evening, depending on his schedule. Me being retired, my schedule's wide open.
Virtual, yeah. I need to do more of that myself. All right, my wife's going to try to help with the lighting, so let's see what we can do here. Yeah, as I said, it might
Welcome to NTWC Live. My name is Alex Garcia. I'm the director of the National Tropical Weather Conference. These programs are made possible by USAA, South Padre Island Convention and Visitors Bureau, and Plylocks Hurricane Clips. To produce these programs, it's a team effort. We have Bill Reed and Tim Smith with us this morning. Here's Tim Smith.
Thank you, Alex, and good morning, everybody. Good to see so many happy folks along with us today on this quiet weather day in our part of the world here in South Texas. Beautiful sunshine outside the window. It's a gorgeous day. We want to thank all those sponsors that you mentioned, Alex. Of course, Plylocks, USAA, and South Padre Island. I was on South Padre Island this weekend. So were a whole lot of other people. Trying to practice social distancing best you can. Be safe out there, folks. It's a good idea. But thanks to all the sponsors for making this a possibility. We appreciate it. Another great program for you today, and another of a series of great programs we've had, but I think you're really going to enjoy it today. Some fascinating stuff coming up. To do the official introduction, let's turn it over to our Master of Ceremonies, the host with the most, former director of the National Hurricane Center, Mr. Bill Reed. Good morning, Bill.
Good morning, Tim, and everybody following us online. Much quieter in the Atlantic this week than when we were talking about it a week ago. No tropical cyclone development is possibly at least 5 days and maybe even longer than that in the weather pattern that's showing up for the Atlantic. There is an interesting feature. A large area of dust that started coming off of Africa a week ago is making it to the eastern edge of the Caribbean islands and will overspread that area this weekend. And the aerosol models are showing it reaching Gulf Coast of the U.S. and maybe South Florida mid to late next week. So that'll be one thing to keep an eye on. And it does cause problems with people with respiratory illness, so it does have some significance. Eastern Pacific, there's only a slight chance of development, probably over the weekend and early next week. And it's well away from land and will not be impacting anything but shipping if it does develop. Our guest this morning is Cione, and he's coming to us from Boulder, Colorado, where he's been detailed out there since 2014. His home assignment is actually the Hurricane Research Division back in Miami, Florida. Joe has all his degrees, culminating with a PhD from North Carolina State. He specializes in the physics of the boundary layer over the ocean, and to look at that stuff, he uses remote sensing. I first became aware of the use of drone technology when I was at the Hurricane Center some 10 to 12 years ago, and since I retired, I haven't really been keeping up with it. So I'm looking forward to what you have to tell us of what's new in the world of unmanned aircraft observation. So it's all yours, Joe.
Hey, Bill. Yeah, thanks for the intro. I appreciate it. Yeah, you mentioned the beginnings of drone work, particularly for hurricanes, and it's been a while. Our first missions were in 2005. I don't know if were you there, Bill, at the time? Were you a director in 2005?
No, I was detailed there in the summer of 2007 and was there from 2007 until 2012.
Okay, so yeah, the first drone mission ever was what we used, something called the Aerosol, which is something that we don't use anymore, and it's a different concept of operations where we would basically deploy people from an island or a location and then send the drone into the storm and then send the drone back. It's pretty remarkable that we were able to pull that off back then, 2005. People talk about dog years, but in UAS years, that's like a century ago. And we did have a second mission in 2007 in Noel. Our first one was in Ophelia. But what we're doing today is dramatically different. We leverage our existing resources, and our primary resource for doing that is NOAA's P3 aircraft, a Hurricane Hunter aircraft, and we use that as a deployment vehicle. So instead of sort of having a drone from some remote location, fingers crossed, hoping it could get into the storm and hoping it can get back, we use that as a deployment aircraft and drop a much smaller drone in the environment and sample while we're there. So happy to talk about what we've done. If you want me to jump in on that, really kind of your guys' call, your show.
Yes, go right ahead.
So we have been using drone technology, as I said, going back 15 years or so. But more recently, since 2014, we have come up with these air-deployed drones, and the company that builds them is Raytheon. They actually, the beginnings of that was a small company, Advanced Ceramics, which was then bought out by BAE, which then went public to a company called SenseIntel, and then eventually was bought by Raytheon, which is where the situation stands now. So we went through a lot of iterations of ownership, but the concept essentially was the same in that, you're looking at a small drone that was tube launched from our, we have something called AXBTs, which is the airborne bathyothermographs that are typically deployed from the P3 to measure ocean structure. So the roots of this technology go back to the Navy. The Navy uses P3s for sub-hunting. And how this happened was at the tail end of the Aerosonde days, I was giving a briefing at NASA. We worked closely with NASA during those early days. And I was really essentially wrapping up what we're doing. We attempted to fly, we got 2 missions, as I said, in hurricanes, but we probably tried about 8 times. And for whatever reason, we couldn't do it. Either the storm wasn't close enough, we couldn't get a team in place, the storm fizzled out, and we had assets. So we knew we were wrapping this up. And I met someone there from the Navy who said, listen, have you heard of this thing called the Coyote? We're using it for sub-hunting. We use the P3s. So long story short, we basically traded assets. They said, we have these drones, we being the Navy. You have a P3, which for technical reasons, they couldn't get access to their own P3 to do testing. They said, you want to try this out? So talking with AOC and people within NOAA, within 6 months or so, we were able to test this drone. The drone itself is a 15-pound aircraft, well, 13 to 15 pounds, 5-foot wingspan, so it's not a large aircraft. In fact, if you want, I can quickly share my screen and show you what it looks like. I'll jump back to talking. I'll jump into that story again, but let me try to share screen. Hopefully technology is our friend. It's not our friend right now. Let's see. Desktop. Let's see.
There.
Okay.
We've got your Zoom screen.
Okay, you got that? Now is that?
There you go.
Are you seeing?
Yeah. Perfect.
Okay. All right. So this is not. This is a talk I had in Boston for the American Meteorological Society, but I want to get to this. So that's a drone I'll talk about in a little bit. So basically everything I will talk about initially is version 1.0. This is what the Coyote. And what I'm holding there is not the Coyote. So in more general sense, what are we trying to do here? As I said, we're really trying to leverage our existing resources. We have emerging technology that's coming out. Technology is constantly advancing, as I don't have to tell your listeners in every respect, including this technology for drones. And we want to basically fly in an area that's difficult to fly in. Now the hurricane hunters can penetrate, and we fly typically at 10,000 feet when we go into hurricanes, but below, say, 5,000 feet, and certainly below 3,000 feet, it's very difficult and dangerous and impossible, really, to have manned assets go that low. So that's where these drones come in. We still want to go down there. Why do we want to go down there? We all live down there, right? We all live in the boundary layer. If you think about it, when these make landfall, we have to know what's going on from a wind standpoint. And the Hurricane Center, where Bill used to work, would be very interested in getting as much data as they could and in high frequency as they could, and in much detail as possible. So if we can get down there and use these drones to fly in very high wind conditions, it's of value to everyone from a scientific standpoint, but also for the public. So our goals are three-pronged. If we don't fly down there very much, for reasons I just said, we want to improve our understanding. We're scientists, and we want to understand what's going on down there. And while we're down there, we also want to improve our situational awareness. What's the situational awareness? Meaning we want to give data to the operational forecasters. We want to have that ability to give them in near real time what we're seeing. The Hurricane Center gets a bevy of information from all sorts of sources, including manned aircraft from the C-130s and from NOAA's aircraft. But a lot of that data is sort of instantaneous. Think of it as a snapshot, a picture. We get drop-ons that drop, give us a profile of what's happening. We have something called step frequency microwave radiometers, which give us right below the aircraft a swath of what the ocean temperature, what the winds are right at 10 meters, right above the ocean, using something called emissivity, basically looking at the foam and correlating that with what wind speeds are. We have Doppler radar, right? But that doesn't go below, say, a kilometer. So it doesn't really get us really low. So this is why we're doing this. We can get down with the aircraft. We can show what's going on, but instead of a snapshot mode or, thinking the dropsons, where you get locations, but you don't get everywhere. Think of it as a donut. I like to think of it as a donut. So this is a visual. So if you have a donut, you have the middle of the donut, which is the eye. And if you think of the edible part of the donut, you have that as, say, the eye wall, where you get very strong winds. So if we're flying through with the P3, we penetrate through. We get observations along those at that altitude within the donut, right? And then we can drop dropsons and think of it as maybe a sort of a toothpick. So you have these 5, 6, 7, 8, 10 toothpicks going through a donut. What we can do with the drone is drop the drone and burrow out the entire volume of that donut, or a good portion, maybe not the entire volume, but certainly within the boundary layer, say below 3,000 feet, and go round and around. The generation that we're talking about now is about a 1-hour aircraft with the Coyote, but I'll get to it in a little bit. We expect the next generation, obviously we still need to test. We're not at the point we can prove it and it has to survive, but we can get upwards of 3 to 4 to maybe even 5 hours of flight. That's a game changer, in my opinion. And I think that's where we're shooting. That's what we're shooting for. And a lot of the lessons learned from the Coyote, extended range, better performance of the payloads, all these things, these scars, battle scars we have from flying these aircraft in the past, hopefully go into the next generation. So that's the overview and really motivation for what we're doing. To give you an idea, sorry about the noise, but that's how we launch it. And the AXBT chute there, as I said, that was used by the Navy for sampling for the ocean. And we said, hey, this is another example of, we have this, let's use it. So that's why the companies that originally were designed to do this, the Coyote, said, you got to fit this. This is our requirement. You must meet this requirement. How does it work once it comes out? So the picture's worth 1,000 words. I guess this is maybe 1,000,000 with a little video. So the nice thing here is they're all tube launched. So it's a tube launched UAS, and everything that I'm going to show you is done that way. Each aircraft is slightly different, of course, the dimensions, what it can do, duration, but they're all launched the same way. So in all cases, we use the P3 to get us there. Let me, since this is working out good, let's just go through this. It won't take but maybe 5 to 10 minutes to get through everything here. So when do we first use the Coyote? This is going back in 2014. This is about a year after I told you about that test where we used the Navy's resources to their drones and RP3 to test it. We had a launch with no payload, nothing, just to show that it would work and we could communicate. And we did that in restricted airspace off the Florida coast, and it worked. So soon after that, and fortuitously, we were able to get some funding through the Hurricane Sandy supplemental. And that's the beginnings of this project. We put in a proposal and we got a handful of Coyotes. And within a year, we had them up and ready to fly, which is really remarkable and a testament to the team to be able to do that. And our first storm that we flew in was Hurricane Edward in 2014. So this, besides being the first time we flew a drone, this is a remarkable storm for many reasons. I would say from my 2-decade-plus career in working within this field and working with the Hurricane Research Division, this was probably the best sampled storm I've ever seen. And this is Edward in 2014 near Bermuda. And as you can see, we operated at 3 places, St. Croix, Bermuda, and Wallops Island for the Global Hawk. So we had a Global Hawk, both of our P3s, our G4, and the 2 UAS. And you can see all the different patterns here. The Global Hawk is in green, the NOAA P43 is in red, and then the NOAA 42 is in blue. And we also have depictions of where the jet, which goes around the storm, our N49 aircraft, our G4. As far as the Coyote goes, you can see there's the orange circle and the X. So we had 2 missions, one in the eye and one eye wall mission. And the second one was an inflow mission where we kind of want to use the trajectory Mother Nature gives us, and we kind of spiral our way into it. So this was a proof of concept, and we didn't know if it would work. Did it work? And it did. It did work. And this is the paper, if you're interested in it, in AGU Journal. We published that in 2016. I'll ask a question that I know I'm going to get. How does this work? How do they work? How does a small little aircraft survive this? So you're talking about, a major hurricane, which Edward was. The analogy I like to use is when you were a kid, well, at least when I was a kid, I would go near a fast moving stream or a river. We had one close by where I live, and I would throw a stick into it or something that would float. And I would go run by as it was going down the stream and see what was happening. So a lot of times it would be, very turbulent. But the one thing that didn't happen was the stick never broke. So we operate the same way here. You're going to have it bouncing around. That stick was bouncing around, and Mother Nature's pushing it backward, forward, getting submerged, this and that. And that's how we fly these things. We don't try to go opposite of what Mother Nature wants us to do. So what do I mean by that? We deploy these in the center of the storm, in the eye where it's relatively calm, and then we go counterclockwise, start a counterclockwise rotation, and then merge like a superhighway onto into the eye wall region. But when we're in there, we try to keep the winds at the tail of the aircraft. So it's that stick in the river. So it bounces around. And I have a video I'm going to show you at the end that really encapsulates what I'm talking about. But that's the premise, where we don't really fight it, and we allow the system to go and bounce around. One other thing I'll mention, which is better than the stick, is that, and unlike the stick, we have a very smart brain on these things. They look like toys. They're small aircraft, but they have an autopilot. Okay, so that autopilot is constantly correcting that aircraft. So for your listeners who don't, maybe not scientists, this is a 1 hertz measurement, right? Once every second. I can't do what I'm going to say here, but imagine it. The brain of these things goes, the Coyote brain was going 500 hertz. Forget it. I can maybe do 5 hertz. That's about it. So this thing is constantly correcting. So that's how they survive. And you look at it, and say, how does this small thing do it? So the combination of not fighting Mother Nature and having some great technology is really the answer. Okay, so what did we do? What was our follow-up to this? So that was in 14. We had some engineering issues that we had to work through. We didn't have as many opportunities, but finally in 2017, we did fly 6 missions into Maria. So you might remember Maria was a category, I believe 5, yes, either 4 or 5 when it hit, Bill could maybe help me on this one, when it hit Puerto Rico and devastated the island. Very, very sad damage and situation that was there. We did not fly during that time. We flew, you can see where we flew. We flew our Coyote missions well after that. Coyote Flight 1, 2 to 4, and 5 to 6 in this region. But it was a major hurricane. So all 3 storms, Edward, the missions here in Maria, and also which one I'll show you in the next one here, over here in Michael, were all major hurricanes. So we had 6 flights in that, in Maria, and then 1 in Michael. Michael was a rapid intensifier too. You could see where we started going right as it was intensifying. Very incredible storm. Also, Michael was where we got our maximum winds, 87 meters per second. That's not a typo. 87 meters per second at 640 meters. Also, these vertical velocities are incredible too, plus 14, and we also had minus about 12. And again, how do we survive that? If you looked at that, if it was that stick I was mentioning, the plane would be bouncing all over the place, and I'm not sure it could survive that kind of violence, but it's correcting for it. So even though we're getting thrown up and down, or the Mother Nature wants to throw us, the autopilot is maintaining that. And this next image really shows that. So you can see this. This is that Flight 7. So as much as we're getting thrown around, this is elevation, altitude. So this is 500 meters. This is 750 meters. So we're getting thrown less than 100 meters, even though we're getting tremendous vertical velocities during this period. And the scale here, you can see the winds on the right here. So this is, you can see the darkest red are associated with that flight. So this is our most violent emission by far, but we're also at a high altitude. Another one I want to show you here, this is one of our most interesting flights, and we're writing up papers. We have a BAMS article, if you haven't seen that, the Bulletin of Meteorological Society. That's a second paper that encapsulates all this data and all these flights. But we also have other spin-off work that we're doing, and one of them is for this flight, which is flying very low in hurricane winds. And where this set the record for maximum winds for a drone, this set the record for lowest flight capability in any aircraft. Right? As I said, about 100 meters. I will show you a little video that probably will get your viewers pretty excited. It gets me excited, and I've seen it many times to show what that looks like flying that low. But you can see our pattern here. What do? We kind of level off, we fly, and then we go down to a different altitude, and we try to get measurements at these different altitudes. It allows us to get, particularly when we get very low, we can do stuff like surface fluxes, and we can look at surface fluxes are essentially, you can think of, how the storm feeds itself, how the energy comes out of the ocean, and how the momentum is transferred down to the ocean. So this is critical for our understanding. It's also critical for how the computer models simulate these storms and how they can give us better estimates, particularly of intensity change. And that's some area that we hope we can improve the physics of by these flights. All right, so since we're just going here logically, everything I showed you was from that version 1 of the aircraft, our technology. There were some things that were not good. I showed you a lot of things that were good. We couldn't fly more than 20 miles from the mothership. So when we dropped from the aircraft, we had to stay within 20 miles. That's very, very restrictive. And a lot of times 20 miles was probably the maximum. Sometimes the payload worked, the meteorological payload, particularly pressure, temperature, and humidity. Sometimes it didn't. We learned a lot of what we can do, and what we can't do. Remember, we're staying up a lot longer than a dropson. A dropson has been tested for 20-something years. We have similar sensors on there, but you're not up for an hour, and you're not flying horizontally. So a lot of the different conditions made us look at this differently, and we think we've made a tremendous amount of improvement, and the requirements put on these new aircraft that I'm going to go through here have to jump through significant hoops. So the bar is much higher for them, but if they can reach those bars, I think the confidence level that what we're going to get is going to be tremendously advanced. The biggest advancement you see for this Area I aircraft, this will be the first one, fingers crossed, that we're able to test. There'll be 3 that I'm going to describe here. This is a 27-pound aircraft. Just for remember that the Coyote is half that weight, about 15 pounds, 13 pounds to 15 pounds. The Coyote at max can do 1 hour, 4 hours. We might even be able to get as high as 5 hours. So somewhere between 3 and 5 hours. The cruise speeds are about the same. This thing has an 8 to 9 foot wingspan. It's actually retractable depending on how bad turbulence is. So we can retract these wings. You get a little less endurance when you do that. We have payload here. We didn't have payload in the Coyote to speak of. It had a little bit of a payload, not 3 to 6 pounds. Someday, not now, but we might be able to use some of this payload to enhance that number. So in other words, hey, we don't have a payload, but we want more batteries, and we can go higher. Can't do that right now. There's some technical reasons. So we're kind of, quote, stuck. Believe me, I'm not mad about being stuck to 3 to 5 duration when we've been working on 1 hour duration, but we can maybe even go beyond that. So we're excited about this aircraft. We are in CAT mode, and what CAT mode is clear air testing. So we don't want to jump into a hurricane. We have to make sure this thing works. We do ground testing, which a lot of ground testing has been done, but then we do clear air testing with the P3 to make sure that this works. We're hopeful that we're able to continue our clear air testing this summer. And then if that goes well and we can do the testing, we're all in trying times. I don't have to explain that to your viewership, where it's, we're doing the best we can. And we are hopeful that we can test. And if not just test, but if those tests go well, can it communicate 150 nautical miles? Does the payload work? Is the comm system up to snuff? Can it survive a launch? Something like that. It's getting shot out at 210, 215 knots. Can it survive? These are things that the Coyote has done. None of these have done that yet. This one, so keep in mind, remember that was 27 pounds and the Coyote was 13. This is 9 pounds. This looks like the Coyote. This is Barron Associates. The interesting thing about this guy is that they're already at 2 hour endurance, and they're smaller. Sensors across the board. First of all, they make a good sensor. Second of all, NOAA uses this for the dropsons and the balloons. We want to stay consistent, right? So we know the air characteristics, we know what we're using. And this also allows us to when we get to the point of assimilation, data assimilation, which is not, that's down the road. We also should have the ability to do that easier because we're using the same payloads across the board. So as I said, this is very similar schematic. You get the parachute, it comes out from the tube, from the XB2 tube, has a double wing pattern, which is different than the Coyote, but it's very similar in many ways. So this is the last one. So I gave you two. This one is Black Swift Technology, a company out here near me in Boulder. They have an S0. They have an S2 that they've much larger platform that they use and had successful launches with and campaigns with NASA. This one is tiny. This is between 2.5 to 3 pounds. So I'm a little nervous about this one. The engineers say don't be, but because of just it's so small. But it is pretty remarkable if this, and we're excited to test it. Again, same sort of launch, it's a parachute. I should mention, I didn't say this, the only one without a parachute is the biggest one, does not use a parachute. The Area I Altia 600 does not use a parachute, should mention that. So yeah, just a little bit more here, same thing, a 2.5 foot wingspan. The biggest one was 9 feet. So we're between 2.5 and 9 feet, 1 to 2 hour duration is the target. And again, it can handle a lot. These are under NOAA's SBIR program, which is a partnership between the government and private sector. And it's really been a remarkable partnership. There's a phase 1, a phase 2. For the last two, for the Black Swift and the Baron, we're in basically phase 2 for both of these. Phase 2 is 2 years. We're through 1 year. We have 1 more year of phase 2. And at the end of the phase 2, we expect to have prototype to test, hopefully in a hurricane environment. So a lot of great stuff going on, and the summary is that, these can help us improve what we're doing by safely exploring regions of the storm that we just couldn't do otherwise. Again, we got dropsons, but they're up for maybe a minute in the boundary layer. These things are up for potentially hours and doing potentially orbits. So you can get things like radius of maximum wind, a better estimate potentially of Vmax. If we're going out far enough from the storm, we can do other radii too, not just the radius of maximum. Maybe you can get the radius of storm force, or we can sample different areas. We hope to get better situational awareness for the forecasters, improve our understanding, and ultimately to improve the computer models that are predicting the intensity change. This type of aircraft is not going to help us tremendously with where the storm's going, so what we call track, except with one caveat. It could help us by, say, loitering in the eye, necessarily trung these storms and enhancement of today's numerical models. So we're at 500 feet. This is from that low flight of Maria. I mentioned that we were, real excited about that, and I'm working with colleagues to have another publication on that. So you can see the altitude. We're at 400 feet. It's not meters. Winds just right now, I'm reading it, it's changing every second, 89 knots. So we're in hurricane force winds at 100 meters or so. And you can see how this thing bounces around. This is the ocean, this is the atmosphere. It's incredible. And also, one other thing, this is every 6 seconds. So this is not, what you're seeing is not real time. So for every second you see here, it's 6 seconds of real time. Still, you see these pitches and rolls of 30 degrees, 40 degrees. And the plane stays up. It doesn't just say, tilt over. And I think that a lot of that has to do with that very big brain it has inside there. It has the ability to make micro adjustments, very, very, very quickly. As I said, 500 hertz. So 500 times a second, this thing can change and adjust how the aircraft is flying. And I think, honestly, I don't know if 500 hertz is necessary, but you need a pretty good brain to be able to do this. I'll stop and talk or listen for questions if you guys want, or let some other people talk. But last thing I would say here is watch for at the very end. It actually does a 360 and stays aloft. It recovers not very long, for maybe about 3 or 4 seconds after that before it goes into the drink. And you'll know when it's in the drink is when you only see a brown screen there. So anyway, with that, that's kind of all I have. I'd be happy to expand on what I talked about, or if I missed something you guys want to ask me, I'd be happy to do it.
Airspeed.
Fascinating stuff, Joe. Thank you for that. I'm watching the Facebook comments come in, and the thing that I'm seeing most are basically just people's jaws dropping because they're amazed at what you're doing. I see a pilot just posting cool from Sunny. And Vanessa said, I didn't think a drone would survive the wind speeds. I think that's so true. Rich Johnson, one of our regular viewers, says sometimes when a tropical cyclone makes landfall, the winds indicated by the drop sign aren't indicated on land ops. It seems like this program would be extremely useful by sampling very low level winds to better predict before landfall.
Yeah. Well, one thing that's interesting to me, and this is something I've mentioned to some of the forecasters at the Hurricane Center. And again, so everything I'm going to say here is predicated on these new platforms working. Okay. So, we have a lot of hope that this will become something routine within the next few years. But it's going to be a lot of boxes have to be checked. But one thing that's really fascinating to me about this new technology is that the way we measure now, right? Let's talk about winds. The way we measure winds at very, very low altitudes is we really don't have tremendous amount of tools with regard to even the manned aircraft. So the manned aircraft's at 10,000 feet. As I said, we can measure up there. We can get the volume of winds from the Doppler, but not below a kilometer, or not really very low. How do we get very low? We have step frequency, which is remotely looks down to the sea surface, as I said, and looks at the foam and gives us an estimate of what the wind is. But again, that's right below the storm, below the plane. So as the plane turns, so you get a figure 4, if you might imagine in your mind, going through that donut, but you get the winds right below that. And dropsons, well, the P3 has to drop the dropsons too. So you get dropsons right there. And you definitely get the detail we get from that is absolutely amazing. But one of the things that's always kind of bugged me is that we want to sample more. We want to sample the volume. We want to go around and around. We don't just want to have a point here and a point there. So I think that this type of technology allows us to get more of a continuous look in areas that we actually would physically never sample because we're just not going to be able to get there. The other thing too is that Vmax is an interesting parameter. Vmax is the maximum wind in the storm. That's something the Hurricane Center wants, right? And we understand why, because you can get an estimate of what the worst case scenario is. That has engineering aspects, that this thing makes landfall, what damage is it going to do to structures and people and everything. So completely understand that. And my thinking, this is me, I'm not speaking for NOAA, I want to be very clear, but this is something I think we're going to potentially get from this platform, is that if you look at, I can use my hands, you can tell I'm Italian, I use my hands all the time. So we got a bell distribution, right? So you got a normal curve, okay? People, and what that is when you do something like that, right in the middle there, that's your median, right? So you've got your average. So we probably are measuring the average conditions. We certainly are measuring, but when you talk about Vmax, that's the maximum. It's not asking you the average. It's saying, what's the maximum wind? So you're out by the tail. You're out over here, right? That's what we want. But we're challenged right now to measure like that. So I think that this type of platform, by going round and around and being continuous, is going to push us to be able, I don't know how far out that curve, but closer to where we want to go for that Vmax, to better estimate of what that is. And I think that could be a potentially very valuable thing. The only other caveat I'll say there, though, is that when you don't measure something a certain way, and when you start measuring something a certain way, there'll probably be some skepticism. And for me too, first of all, is it measuring correctly? And what are we measuring? So there's going to be probably some education going on to say, we might start measuring a little stronger than we thought because we weren't measuring. We'll have to see. But I think regardless, I think it's going to be a very exciting time. And I think if we can get these types of platforms, we're in R&D mode to the point where we're operational and we're doing it all the time. I think that really we have a potential to be a transformational observing platform, sort of like the Dropson was. Dropson came online in 1997. This can be that step function jump if we can get this type of technology. I got my fingers crossed, and I've been doing this for many years, and I'm hopeful. That's really what's pretty exciting to me about getting us to the next level.
Bill, jump in here because this came along after you were at the National Hurricane Center, right? This is stuff that when you were there wasn't quite doing this just yet. Dropsons, but not so much the drones, right?
I had the Aeroson. In fact, the first one of those I saw, they have one of them on a stand out in the lobby at HRD, and I said, "This is cool." And that's when I think it was Frank Marks gave me the rundown on what all we're trying to do with that. A couple of things here. I noticed that the flights you flew were generally well above the level that we actually estimate what the maximum velocity is, which is the 10-meter wind. But how do you account for all how do you think you're going to account for all the variability you see in the dropsons in that 500 meters down to the surface that we see in the wind fields in that when we start getting more data from these?
Yeah, no, that's a great point. For obvious reasons, well, two things. We're definitely in R&D mode. So everything we've flown now has the duration of, if you remember that slide I had up, somewhere between 30 minutes and 40 minutes, and sometimes even less than that. So we really don't have a lot of time to be able to get all the levels. We think that's going to change once we have this new generation of being able to fly hours. So I think we'll be able to go lower earlier. Now, 10 meters is going to be difficult, especially when you got flight assignment is to have a laser altimeter on there, so that we'll know instead of just a GPS, so that we'll know exactly how high we are. Because if the ocean's doing this, 10 meters or 50 meters, whatever we are, is changing it at all times, right? So we're probably going to have to do also, Bill, you can, if I don't explain this well, maybe you can jump back in. When we fly the manned aircraft at 10,000 feet, we have these height reductions, right? So we'll fly it and we'll reduce it based upon some certain percentages that past work has shown, is good. We could do, and I expect to do, similar height adjustments using these drones and having the drops on still important, where we would have drops on information, and also step frequency is probably just as important. So we can potentially have the drone flying low, right? This is something I was thinking of as a mission. And then the P3 at 10,000 feet, or as low as we can get, for portions of our flight, it can't, because they're two different aircraft moving at different speeds. So it's going to be logistically difficult, where we can get over dropsons hitting us, not hitting us literally, God, no. And that the odds on that are low anyway, but also having SFMR measurements that are coincident. And then I think we can maybe make some algorithms and some relationships to say, okay, a UAS at 500 meters, it's 95% of the wind, or it's 92% of the wind. We're going to have to do that. But we should also be able to, because we eventually go to zero, we should have some legs at really low altitudes, 30, 40 meters. And eventually at 10 meters, if we can get there, if we can do the altitude deal with the stuff, with the laser, that we should be able to get some direct measurements and then comparisons with SFMR and the dropson. I think that's 10 meter. But, I think that there's other value besides just getting the 10 meter wind too, that could really help us with regard to, looking at the radius of maximum winds dependent upon the quadrant, let's say. So we can have azimutally high resolution estimates of what their RMW is at an altitude, at various altitudes. We can see things like tilt and see how that changes as we go around the storm. And that's something that is harder to do with the technology that we have now, I think.
Cool. Yeah. Now, flying this thing is the operator in the aircraft giving it commands for the basic turns, or do you program that into the device itself?
Great question. And that's something I did not touch on. So we gave these guys, all three of these new companies, lots of metrics. Hey, you got to fly 150 nautical miles on your own. We can't babysit you, because the P3, when it flies, it does these 100 nautical mile legs, right? So we want to drop it and forget it. So ultimately, they have to be able to be communicate without having the P3 babysit, like you saw in that last video. So that's one. The second thing is right now, for everything we've done with the Coyote and for the first flight drops of these new drones, we will have a pilot and an engineer on board that will be saying, working with me and saying, okay, let's drop down to 500 meters. They will put waypoints in there. So they'll give a lat long point and it'll go to it. And we'll know, because we have the situational awareness on the P3, and we'll basically tell it what to do. But that is definitely not the future. The future is going to be artificial intelligence, machine learning, And this thing is it's not going to be a pre-programmed pattern, not like drop it, okay, do a circle, see ya. No, it's going to be, for example, I'll give you an example. We drop it in the eye. It'll have the sensors on there, pressure, temperature, winds, humidity. So we will say, okay, the code will be hard written to say, okay, begin in the eye where it's relatively calm, start doing a counterclockwise rotation, generally speaking. So let's say we want to get into the eye wall. We would say, okay, you're doing this orbit, increase your orbit. And as you increase your orbit, you're getting closer to the eye wall, right? Where your pressure should be lower on your left, and pressure should be higher on and your wind should be increasing on your right. So these are all meteorological things we know that we can use for coding. And as it does that, it uses the sensors there and says, okay, I see the winds are increasing. I'm going in the right direction. Let me keep increasing my radius increasing. And before you know it, now you're in the eye wall. And now you're circling in the eye. And let's say we want to find the radius of maximum wind. Keep going. So the code would say, okay, you found these strong winds, keep going until they decrease. Why decrease? Because we want to find the radius of the maximum winds. And the only way you find the maximum is if you hit the maximum and it decreases. Then you know you hit the maximum. So if you can imagine in your mind's eye, now we're going around in the eye wall. We're not just going around a circle. We're doing this S pattern. So you're constantly finding where the edge of that radius of maximum winds are as we go around. Now, this is just one example to show how the automation would work. The other one could be, another quick one would be loitering. You want to hang around in the eye for 4 hours and maybe catch rapid intensity change. How does that work? Because you got a mass field and pressure, and then you got a wind field, right? So as the pressure changes, as the storm intensifies and the pressure goes down, what's the change? How does that work between that change and then when the winds change? Is it instantaneous? Not, but what are the lags on that? So there's a lot of different things we can do, including hanging around in the storm center, which is something that I was told Ntwc is interested in, doing center fixes, eye wall, trying to get a better estimate of Vmax, doing radius to maximum winds. So whatever we do will require the sensors on the UAS to figure it out. And there'll be different modes. So we might not be able to we drop it and say, all right, we're going to do an inflow mission, which is 300 miles away from the storm, follow an inflow channel as Mother Nature comes in and guide your way into the storm. That's another mission, by the way. I can talk about that more. So it depends on what we want to do. But my goal is to have 3 or 4 of these things we can do scientifically. And when we launch it, you drop it and forget it. We're not there yet. And I think when we get to the operational standpoint of routine, we will be there, because we don't want to babysit these, and we don't want to sit there and have to have, an engineer on board telling it what to do.
Very cool. I would guess the major advancements in longevity of flight are coming from these up and coming advancements in battery technology, so you get better storage without adding weight.
Yep. Yeah, that's exactly true. And Elon Musk is our friend. He's really kind of transformed almost single-handedly the whole battery industry. The interesting thing about the battery, that's not my area of expertise, but one interesting thing that, these are not, we don't recover these drones. It's just, when they hit salt water, first of all, electronics and salt, not a good combo. Very high winds. You can imagine when this thing does tumble, it's snapping in half. How would we recover it? We certainly can't recover it in the P3. And, anyone that's been on a boat knows that you don't want to go anywhere near a storm. Hundreds of miles, you get waves that are incredible. So it's something that's just not really recoverable. So one thing that's interesting is that a nuance of the battery technology is that when you have reusable batteries, they're reusable, but the maximum endurance is not as good as one-time use batteries. But we're only using it once. So we get an extra bonus from that, because we aren't using the reusable batteries, because we're our one-use system, and we take advantage of the fact that right now the longest duration batteries are the one-use batteries, and that actually, it used to be a little bit better than the reusable batteries, but now they're a lot better in some cases. There's also some other technologies, the exotic technologies that are maybe on the horizon that could give us even more duration. But at this point, yeah, we're looking at somewhere between 3 and 5 hours for that larger aircraft, and 3 hours even for the smaller aircraft. which is remarkable. If we go too long, Bill, we have to start thinking about other things. So let's say we can get 8 hours. Well, the P3 can't last 8 hours out there. So what do you do then? So one thing we're doing with that is, and we're already testing that, this is not near term. This is, everything I'm talking about, getting it operational. This would be next generation, probably version 3. We have the ability to use satellite communications, but they're not robust enough yet to get the data, to do all the telecom stuff that we need it to do. But if we ever get to the point where these things are really robust and can stay out there really long times with battery technology like that, then we would have to rely upon using satellite technology as its primary. Right now, the two small ones don't have any satellite technology on there, and the large one does have it as a backup, as an emergency system. So there's potential there. But that really doesn't come into play, in my opinion, until we get the durations that exceed P3 on station time.
Long time away, probably. I guess the inquiring minds want to know this ultimate question: what's the cost per unit while we're developing this?
Fair enough. So the cost per unit, one of the metrics I gave, I said, you know what, this is hard. I'm not an economist. So I got to be careful with, anything talking about money. I'm a scientist, right? But, like everything, it comes into play. So I started thinking, well, how, the Dropson's $900. Now the Dropson is not the perfect comparison, because, you're talking about this versus this. I think a better comparison, from a data collection standpoint is manned aircraft. But let's just go with the closest thing we have, because both are expendable. So you're talking about $900, and you're talking about 5 minutes in the air when we drop at 10,000 feet. But in the boundary layer, which we're really interested, right? That's why we're dropping this thing to get in the boundary layer. You're talking about a minute. So, maybe 2 minutes, let's say. Let's even be generous and say 3 minutes. I don't think so, but let's just say that. You're talking about $300 a minute. So I put that as a metric that these things have to beat that. And so if you're talking about $300 a minute, all three of these platforms beat that. We want to get the two smaller ones less than $10,000 a unit and flying multiple hours. And if you do the math on that, everyone go get your calculators. It's less than $300 a minute. For the bigger one, the cost is more. For that one that I said that can stay up to 5 hours. But see, we wouldn't use that. We would use that. I'd like to have all three in the toolbox. It was up to me, which it's not. But if it was, I'd like to use that so that we have it as a toolkit. So, for example, if we had a landfalling system where we were worried it was going to go from a 3 to 5, the models were saying maybe we're going to get a 5 and we're out, 12 to 24 hours. You might want to throw the big guy out there and say, let's have this thing really see what the winds are, doing 3, 4 eyewall orbits, because we have 5 hours to do it. Or we really want to look at the turbulence structure in this storm and compare it to look at closure schemes in the numerical model. So we need that payload. So we're going to fly that guy, that bigger one, to get model enhancements. So I think there's a use for everything. But for the smaller ones, for the routine ones, under 10,000, and by the way, right now, with both of those smaller ones, we're at 3 to 5,000. Now, hold on, that's not what we could buy them for, but that's the build cost for them, which is better than I thought we would be. And I told them 1 to 2 hours. Both of them are at 1.5 at a minimum, and one of those platforms is thinking 3 hours is very possible. So they're overachieving. So from a cost standpoint, I think we're really in good shape. One other thing I'd like to say, especially to my Dropson friends, look, I am the biggest caveat. I love the Dropson. It's a transformational platform in its own right, particularly when it came out in '97. So it won't go away. And I think like that tool kit I said, we're going to always have those. There's going to be always going to be a need for the Dropson. But as far as funding this goes, the next generation, we could look at a situation where, say, we drop 30 Dropsons in a storm, and sometimes we do that. What about we drop 20 in one storm, hypothetically? Well, now you didn't drop 10, and that's about $10,000, right? So how about we, in that scenario, we drop a drone that cost us maybe $8,000 or $9,000 and lasts for 3 hours. We didn't spend an extra dollar. We still used the same amount of money. We just took 10 Dropsons, which you could argue that one drone is going to measure potentially, well, differently, definitely, but maybe just as much or more than those Dropsons did. It'd certainly be up a lot longer time. And we didn't spend any extra money. So I think the future of this, you could partially, at least partially, I don't think that's the full answer for the funding part of this. And again, that's out of my bailiwick. That's up decided by NOAA. I don't get into funding decisions, how we get money and all that. That's out of my area. But if you look at it that way, though, that presents an opportunity in that we could look at an advanced technology and using at least some of the existing resources we have to do that and still keep the drop-ons in play. So I think that hopefully something like that keeps everybody happy. Because I know, and I've given talks to a lot of my friends who are real drop-on proponents, and they get worried about seeing this like, this is going to replace the drop-on. I'm like, I've never said that. So I'm going on record as never saying that again. But it is both. I think both working together would be great.
Fascinating stuff. You've answered all my questions. I'm going to pass it back to Tim Smith.
Okay. Thank you. Well, I've got a couple of them coming in on Facebook. I want to ask you those because they're interesting. Eric is asking, first of all, he says, thanks, it's fascinating stuff. And I think that's been the common sentiment here. But he says, do you think in the future it'll be possible or desirable to deploy the drones from ground level in landfall zones?
I am friends with Forest Masters. Okay, you guys may know him, may not know him. Those are weather weenies like us know. He has been storm chasing landfalling hurricanes for 20 years. And he reached out to me, interestingly enough, about 6 months ago. They can do everything. Those guys put up towers. They know how to get into situations. They're safety first. So they just know how to do it. And he approached, he said, look, I know you're going to be doing these air deployed, but what do you think of a land deployed UAS? It would be different than what we're talking. It would be probably not similar in concept, but it would be a different type of drone. I'm open to it. The hurdles there are one giant one. It's how can we get clearance to fly from the FAA? Flying a plane and letting it go, we need to have a lot of safety restrictions and go through a lot of hoops there. Landfalling, I think it's not an issue. One thing I thought of, just, again, this is just me spitballing, is, as you have a landfall system, you have onshore flow, right? So onshore, and then you have offshore flow. So potentially what we could do is launch this as we have offshore flow to specifically push this thing offshore. So we measure it as it's coming on land, and it would still be land, and then you would transition to the ocean, and then maybe have it wrap around and then kill it before it comes back on land. That's something we could. I think that's the lowest hanging fruit. I don't think there actually is any low hanging fruit. Maybe it's you have to reach up, kind of get the fruit, but it's possible. And I think that it's fascinating. And I'm going to work with Forrest and others to try to see if we can do that in the coming years.
We got a comment from Sonny, who's been watching all along. He says, you're going to have to up the mass of the craft and have the wings that can flex and do its best to go into areas of interest. And he says, looks like amazing stuff. Yeah,
well, I'm not an engineer, and that's the biggest unknown. I actually didn't think the Coyote would work. I was very much from Missouri on that. I did see the Aerosonde work, so I had some confidence it would go. But where we wanted the Coyote to go, there is flex. You need to have some flex, but you also have to have a pretty smart brain that can correct for all those deviations that are constantly occurring. I think that's sort of the secret sauce of how these things stay up.
Great stuff. Thank you. Bill, any other questions on your end before we wrap this up? It's good stuff.
I'm happy to hear that.
There, I'm unmuted again. I was talking to myself. Yeah, Joe, it's great hearing from you, and look forward to following trends in this. We'll get you back from time to time to update us as the seasons go by.
Oh, absolutely. Thank you. Thanks for having me on. I really appreciate discussing this exciting time. There's a lot going on, and as I said, I think we're at the precipice of really having a next leap, and it's not just going to be one of these, it's going to be a step up. And I think both from a real-time operational standpoint, an understanding standpoint, and then my goal is to get to the point where these are routine, that people almost yawn when they see these, like, oh yeah, there's another drone and a hurricane, big deal. We're not there yet, but then I know we made it when we get to that point. Great stuff, Joe. Thank you so much for it. We really appreciate it. It's the future
hurricane tracking, forecasting, it's all right here, and it's right there. So we appreciate all of your work to make this a possibility, and thanks for spending time with us today to get the word out about what you're doing. We sincerely appreciate it. Good stuff.
Oh, anytime. Thank you. Thanks for having me.
All right, Alex, back to you.
All right, let's talk about what's coming up for tomorrow on NTWC Live. Again, another thanks there to Joe. Appreciate it. It was a great program. We've got Dan Kotlowski from AccuWeather tomorrow. He's talking about hurricane operations there at AccuWeather. That is at 10 a.m. Central Daylight Time. And again, want to remind everyone that our sponsors are USAA, South Padre Island Convention and Tourist Bureau, and Plylox Hurricane